Yes. Hello my dear students. I welcome you to NEET World. So today we will be discussing hydrocarbons. Okay. So in the last sessions we have already covered complete GOC, which is required for organic chemistry to understand organic chemistry more effectively. So that GOC part will be highly helpful. Okay. So from that particular topics which we already discussed, you can expect 3 to 4 questions, and those topics are very basic to understand all the remaining topics of organic chemistry. Okay. So let us start our hydrocarbons here. So from this topic you can expect at least 2 to 3 questions in the upcoming NEET exam, and also in EAPCET you can expect 2 questions. Okay. So let us start our discussion. So today's discussion will be including preparation of properties of alkanes, preparation of alkanes, like properties includes chemical, physical properties and all the chemical reactions which are shown by the alkanes, and also preparation methods for alkanes. Then we can move for the alkenes preparation and their properties, then also after that alkynes. Okay. So this is what we are going to discuss today. So in this session I am also including the previous year questions of NEET and EAPCET. Both it will be helpful for both students who are preparing for NEET exam especially, and also EAPCET of Telangana and AP students. Okay. So let us start our session. So first one is how do we prepare? So methods of preparation of alkanes. Preparation of alkanes. So there are different methods. So the first most and important method is this one. Okay. So first one is Sabatier-Sandrans process. Okay. So let me show you. Yeah, Sabatier-Sandrans reaction or the process. So what exactly here? So using unsaturated hydrocarbons, from unsaturated hydrocarbons. So what are unsaturated hydrocarbons? I can say from alkenes and alkynes, by hydrogenation they will produce alkanes. So alkenes upon hydrogenation, so H2Na, nickel. Okay. So this is a metal catalyst. So on that we are using hydrogenation like H2 gas here. So that will gives us alkanes. Okay. So let us see some reactions here. Okay. So first of all let us take here we have alkene like this, CH2. So these upon treating with H2 hydrogenation like this, okay, using nickel catalyst and hydrogenation, the H2. So the nickel is a catalyst here that provides a surface which on this H2 gas is adsorbed. Okay. So by adsorption phenomena, now that will be added at this double bonded carbons. Okay. So it means two carbons having like this double bond is there, that will convert into sp3 hybridized carbons. Now we will be getting CH3. So alkene converted into alkane, ethene converts into ethane. Okay, like this the process happens here. So now here you need to remember this is a concerted reaction. So concerted means reaction takes place in single step. Okay, and here this is a cis addition reaction. What is that? Cis addition. It means both hydrogens. See, if I write this with white color, so both hydrogens which we have had added here, that should be added from the same plane. So it means cis addition we can say, syn addition we can say. These two hydrogens should be in the same plane of the carbons. Okay, both carbons. Now next. Okay, so which is more reactive here? So if I write this is alkene. Okay, this is one alkene. Then next one I am writing here CH2CH, CH3 double bond, CH3 I am writing, this one I am writing, and the next one I am writing here like this, CH3. So reactivity of these alkenes in this process, in hydrogenation process, tell me. So which is more reactive means less stable alkene, more reactive. What I am saying? Less stable alkene, more reactive. So less stable alkenes more reactive in this process. So reactive in this process. So which is less stable here? See, stability of alkenes is explained by hyperconjugation. What I am saying? Stability of alkenes is explained by hyperconjugation. Now tell me. So we already discussed about hyperconjugation. No? So what is the minimum criteria for exhibiting like hyperconjugation? There should be at least one alpha hydrogen attached to this, like alpha hydrogen should present on this alkene carbons. So these are the alkene functional group carbons. So this is the alpha carbon, here also alpha carbon. Therefore here we have 3 hydrogens which are alpha hydrogens, here also 3. Total 6 alpha hydrogens are there. So it has 6 hyperconjugative forms. So more the number of hyperconjugations, hyperconjugative forms, more is the stability. Here you can see, here this side 6, this side 6, this side 6, this side also 6. So total 12 alpha hydrogens are there. Therefore it will be stabilized by 12 hyperconjugative forms. So it means this is more stable than this, and there is no alpha hydrogens to stabilize this alkene. Therefore this is least stable. So what I am saying, less stable alkene, more reactive. Therefore 1 is more reactive than 2, 2 is more reactive than 3. So this is how you need to write the order of reactivity. Then next, if for example I am giving a compound like this. Okay, so this is a benzene. So on this benzene I am writing a double bond over here and one more over here. Now tell me, what is the reactivity order? What is the reactivity order of this? Reactivity towards this hydrogenation in Sabatier-Sandern's process. So I just want to hydrogenate this using nickel. So let us say this is A, this is B double bond, this is C double, let us say this is C double bond. So now tell me, out of this A, B, C like double bond, unsaturated, these double bonds, pi bonds, which is hydrogenated easily, which is more reactive, that will be hydrogenated easily. No? So tell me, out of this A, B, C double bonds, pi bonds, which is easily hydrogenated in this process? Yes. Okay, so write their order. So I told you less stable or less stable alkene will be more reactive. So now less stable double bond will be more reactive. Now tell me, so these pi bonds are involving in the conjugation by aromatic nature, therefore they are very stable, so less reactive. So I am writing B is least reactive. Then next, when it comes to A and C, how can we identify here? So A double bond is less substituted and C double bond, like this alkene is more substituted. Here it has 3 alpha hydrogens which is stabilized by hyperconjugation, but that kind of phenomena is not observed in this A case. Therefore this is less stable alkene when we compare with C. So less stable, more reactive. So A is more reactive, so in between C. I hope it is clear. Okay, if there is any confusion, you just write in the comment box, we will discuss there. Okay, the next thing is, okay, so here one more thing you have to observe. So what I told you in Sabatier-Sandern's process, we are using alkenes and we are preparing alkanes now. So in this method we cannot able to prepare methane. So methane cannot be prepared by this process because simplest alkene possible is ethane, right? So ethene, by using ethene we can only prepare ethane. So preparation of methane is not possible because alkene, the smallest alkene possible is ethane, right? So from ethane we can only expect ethane. Okay, so this is the simplest alkane we can prepare in this process. Methane is not able to prepare in this process. I hope it is clear. Okay, then next, from alkyl halides. See, alkyl halides, let us say Rx. X represents halides, okay, like chlorine, bromine, iodine. So we can treat this with some reducing agent like sodium borohydrate or lithium aluminium hydrate. Okay, so using this, so sodium borohydrate, lithium aluminium hydrate, so they will provide H minus. Okay, they are the source of H minus, and when this X minus is leaving, so this H minus is added, like substituted in this place, so that we are getting respective alkane. For example, if it is ethyl chloride or ethyl bromide, so if we treat this with this sodium borohydrate, lithium aluminium hydrate, so what happens, this chlorine minus will leaves out, Cl minus goes out, and in that place we can have this hydride ion, So like this substitution takes place, therefore we will be getting CH3 as a major product. That is what ethane as a major product. I hope it is clear. Okay, the next method we have is, so the next method we have here, yeah, CH2Cl. So if we treat this with zinc and HCl like this, so what happens is, see, even chlorine is going out, okay, so like Zn, like zinc, like ZnCl2 it can be, okay, so that gives us, see, just remove this and replace with this hydrogen, so we can expect CH3, CH2 and H. So this is what we can expect here, and we can get ZnCl2 here. I hope this is also clear. So this kind of reactions, you make a sheet of this, like in a sheet you make all these reactions so that it is easy to revise. So I haven't brought complete stories here, so I just wanted to give the main important things that is required for the upcoming exam. So only we will be discussing, or we are focusing only on the very important topics of this hydrocarbons. Okay, okay, so now just wait for some time. I will be we'll be doing some like PYQs also. Okay, so Wood's reaction, so this is one of the most important reaction when it comes to both NEET and EAPCET, especially when it comes to EAPCET. So questions are like, many questions are there on Wood's reaction, coal base electrolysis, and the next decarboxylation reactions. So these are the very important from this hydrocarbons, especially from alkanes topic. Okay, okay, so let us see alkyl halides. What is exactly Wood's reaction? Very simple. Alkyl halides, let us say RX is an alkyl halide. Okay, in ether, so write ethers. What is the functional group? Like how can we write ether? Example, ROR. Okay, so this ether should be dry ether. Okay, alkyl halides in dry ether upon heating with what? Sodium. What we are taking? Sodium metal. So this provides alkanes. Okay, so whatever the RX you are taking here, so that will be doubled here. For example, I am taking methyl halide, methyl chloride, let us say. So I am treating with sodium in dry ether. So what happens here? So this chloride, this one is there now. So just make the, like, what is the alkyl group here? We have methyl now. So double it. So you just make it as like this. So just take it like this, CH3. So how we are getting this? So take, when 2 moles of alkyl halides treated with sodium in dry ether gives respective alkane. Like, see, when we are taking 2 moles, so this is nothing but a coupling reaction, Wood's coupling reaction we can say. See what, like here, see, CH3 coupling is taking place now. CH3Cl, write one more also, see, this is 1 mole and 1 more mole I am writing like this. Okay, okay. Now see, just remove this. When we are treating with 2 moles of sodium, so just remove this. Okay, if we remove like this, so here we are getting methyl radical, here also methyl radical, therefore it is getting as methyl radical plus methyl radical. So when you make a bond here, so it will becoming ethane. So like this you need to understand here. I hope it is clear. Okay, now what if we take 2 different alkyl halides, let us say RX and another one is R-X. So what are the types of products we are getting here? DE means dry ether, let us consider. Okay, so what I told you, you need to remove this X and this X and reconnect these 2 things. Just join or connect these 2 things. So we can get R dash as a product, one product. Now see here, when I am taking RX in the reaction beaker or whatever we are taking, their R-based flask or anything. So in that we can have RX molecules, R-X molecules now. So when they are cross coupled, we are getting R dash. When this RX coupling with itself, we can get a RR product. Okay, so when this R dash X is coupling with itself, we can get R dash as a product. It means if we take, when we are taking methyl chloride, and ethyl chloride, CH3 CH2Cl in dry ether. So tell me, what are the products we can expect here? So methyl chloride, it itself can couple and can get this methyl, that is ethane. So now ethyl chloride also it itself can couple and we can get CH3, CH2, CH2, CH3. Yes, so this is one product, this is second product, and first product is when methyl chloride is coupling with itself, we can get first. When ethyl chloride is coupling with itself, we can get second. Now you can take the cross coupled product, so one ethyl, one methyl. So when these getting cross coupled, we can get a third product, that is CH3, CH2, CH3. So one is ethyl and methyl. So this is the third product possible. So these are the possible products you should answer while doing the question. I hope this is also clear. Okay. So here we need to use only dry ether, not wet condition. Okay. So because when you are using wet, so here we are using sodium metal now, so that causes exothermic reaction. Okay. Next, that is about Woods reaction. Okay, in Woods reaction also we cannot able to prepare methane because alkyl halide coupling taking place now. So methane contains CH4 only one carbon, therefore we cannot prepare methane using Woods reaction. Okay, I hope it is also clear. Okay, now we are going to get symmetrical alkanes. Okay, I mean when we are taking even number of carbons, we are getting the product as even number of carbons containing alkane. So for example, we are taking even number of alkyl halide, so even number of carbons containing alkyl halides. For example, ethyl halide we have taken C2H5X we have taken. So it is giving butane. Upon complete coupling, it will be giving butane. So even if you take odd number of carbons containing alkyl halide, let us say methyl halide you can take, methyl chloride you can get. Again you are going to get what? Ethane, which is having even. So that is what? The product will be contains even number of carbons when it is in the Woods reaction. Okay. Let us solve this question. Identify the starting material P in the following reaction. So this is a previous EAPCET question. Okay. So whether you are preparing for NEET or EAPCET, it's fine. Just try to answer these questions. Okay. Very helpful for your preparation. Okay. So here see, when we are doing this kind of questions, I will give you one simple trick. See, alkane is given, we need to find respective alkyl halide from these four options. It's very simple. See, what we know, if we are taking methyl halide like methyl chloride, sodium in dry ether, so we are getting double of it. It means CH3, CH3 like this. Alkyl is doubled here. So it means here also identify the half part. See, by identifying the half part of it, so we can expect which type of alkyl halide it is. For example, here I am writing butane, I am writing. So what is the half part it is having? So it is having like this. This is a half part now. So here one carbon, here one carbon. It means it is a ethane or ethyl. So ethyl means C2H5. So respect to halide, C2H5 some halogen is there. So this is our like starting material, that's it. So here also what is the starting material they are asking now. So this is the product they are saying. Just write the structure of product. See, CH, CH2, CH2, yeah. To this CH2 again CH, and this CH we have CH3 over here and here. Similarly this side also CH3, CH3, like this they have given. Okay, what I told you, so take a half of it, just cut it into the two equal halves like this, so we are getting 1, 2, 3 carbons like this. Okay, and here one methyl group, this is a methyl group we got. So to this we need to add one chlorine or one bromine. So whatever they have given, bromine they are giving bromine derivative, so you have taken bromine here, that's it. Okay, so first carbon, second, third. So 2 methyl, so I can write 2 methyl, 1, 2, 3, 2 methyl, like 1 bromo, 2 methyl propane, that's it. So 1 bromo, 2 methyl propane. So I hope it is clear how to identify the starting material in Woods reaction. I hope it is clear. If any confusion, please go back and watch it again, it will be more clear. I hope it is helpful. Okay, next, the most suitable solvent in Wood's reaction is, yeah, what is the most suitable solvent? So we are using only dry ether. Okay, so it means option 4 is correct. Okay, so all this, see, dichloromethane, so these are containing some polarity. So due to this polarity, reaction conditions are not suitable. Okay, because sodium is a highly, like, causes high exothermic reaction, so that should not be affected the reaction. Okay, I hope it is clear. The next, see here I have mentioned one more question, so just take a screenshot of this, we will be discussing after some time. So this is a direct question, you can remember the suitable reagent for the conversion of methane into methyl iodide. See, I haven't discussed this topic till now, like we will be discussing in the upcoming like within some minutes or in the next class. So this is what we need to convert here, methane to methyl iodide. So using for this conversion, what is the suitable reagent they are saying now. So here itself I am explaining. So for this, iodine is required, so it means definitely there should be iodine, and some oxidizing agent should be there. So here the preferred oxidizing agent is HNO3. So I2HNO3 is suitable reagent for this conversion. Okay, so this will stop the forward reaction of, like, conversion from I2, like it will be having like reversible reaction that will be like stopped by this HNO3. So oxidizing agent like HNO3 or HiO3 is preferred during this conversion. Okay, we will be discussing about this kind of reaction after some time. Wait. Next, alkane which is next to methane in homologous series. So homologous series means, see, there should be difference of CH2 unit. Homologous series means, for example, this is methyl, so the next homologous series contain like this one, ethane. So the alkane which is next to methane in homologous series can be prepared from which of the following reactions? Yes, so this is also based on Wood's reaction only. See, when we are taking 2 moles of methyl bromide, so it will be giving, like, couple that methyl groups, so therefore we are getting CH3, CH3, this is ethane. Yes, I hope it is clear. Next, so this reaction is called decarboxylation. So after, within some minutes we will be discussing. Next thing is we are going to discuss about this, so just hold on for some time. So from this we cannot able to prepare, I will explain why not. Okay, and here hydrogenation, see, generally hydrogenation of alkenes, so generally hydrogenation of these alkenes can be done by nickel, palladium or platinum. So these are the metal catalysts we can use. So for hydrogenation, so add H2 to this, so we will be getting respective alkane like this. Okay, so it can be alkene or alkyne like this. So alkenes or alkynes upon hydrogenation using metal catalyst gives respect to alkanes. I hope it is clear. Okay, so when we are using this nickel, we need to maintain some high temperatures around 200 to 300 degrees Celsius. It is not required for palladium and platinum. Okay, reaction will be taking place for palladium and platinum at normal conditions, but not for nickel. It requires some high temperatures. Okay, I hope it is clear. Okay, the next, so when we are, see, I have mentioned about this reaction. So like this I have mentioned now, CH3, CH2, chlorine, here I have mentioned Zn, and HCl I mentioned. I told you to remove this chlorine and this zinc and connect this ethyl with this hydrogen, we are getting ethane, I told you. Similar to that, so you can apply same story over here. So zinc, see, if it is HBr, so Br, Zn. So I mean Zn, Br2 you can remove like this. Okay, remaining thing is ethyl 1H plus. So we can get ethane. So ethane is produced in reaction 1 and reaction 4, but not in 2 and not in 3, because in 3 we will be getting respective alkane. If it is propene, we will be getting propane. Okay, but he is asking about methane in homologous series, that should be ethane only. So therefore ethane is produced in first reaction and fourth. So 1 and 4, that is option number 1 is correct. I hope it is also clear. Okay, then next, so this about this soda lime decarboxylation reaction, just hold for some time. So this second option, I mean this explanation will be there in the upcoming slides. Wait. Okay, Franklin reaction. So similar to Wood's reaction, here we have Franklin. So in Wood's reaction we have used RX with sodium metal like 2 moles of Rx with sodium metal, and we got RR. Similar to this, this is what the Woods reaction we have seen, dry ether we have seen. Similar to this, here we are taking same Rx only, alkyl halide. Okay, so here also you take 2 moles of alkyl halides, like this I am writing, and use zinc metal. So which metal we are using here? Zinc metal. Okay, so this zinc metal, okay, this gives RR, just couple as like Woods reaction only. Here also you can do like this, RR and ZnX2. Okay, so what happening here? So this Rx, see this zinc, so you are removing like this. Okay, so what is the remaining part? R and R giving RR. I hope it is clear. Okay, so in this method also we can able to prepare what? Alkanes. I mean, we cannot able to prepare methane. So it is suitable for preparation of RR, I mean higher alkanes from lower alkyl halides. Okay, I hope it is clear. So this method is not suitable for preparation of methane. Okay, reaction is similar to Woods reaction. Frankland reaction we can say. What is that? Frankland reaction. So Frankland reaction is used to preparation of alkanes. Woods reaction is used to preparation of alkanes. Yeah, this kind of statement based questions also we may expect. Okay, then next like Corey house synthesis. So here alkyl halides treated with Gilman's reagent. What do we mean by Gilman's reagent? So this is dialkyl lithium cuprate. So this is dialkyl lithium cuprate we can say. Okay, when we are treating this with this, so this is called Gilman's reagent. Very important. Gilman's reagents. What is the formula of Gilman's reagent? It is dialkyl lithium cuprate we can say. Okay, so when it is treated with Rx, so we will be getting, see here one R and this R, so we will combine to form RR. Here R means any alkyl groups. For example, if it is Rx, R dash, so this will be, one will be R dash, another one will be R from here. I hope it is clear. For example, here I am writing methyl chloride and I want to prepare propane. What I am saying? I want to prepare propane. So what is a suitable Gilman's reagent we can use here? What is the alkyl group we required here? See, we have methyl. For that we need to connect one ethyl group. Therefore, I can take here diethyl lithium cuprate. No? So if I use this, so this ethyl and this methyl becomes propane. So this is what happens in the Corey house synthesis. Okay, and this will be very useful for preparation of symmetrical as well as unsymmetrical alkanes. Okay, here also we cannot able to prepare what? Methane. It is useful for preparation of symmetrical, unsymmetrical, both symmetrical, unsymmetrical alkanes. Okay, so depending upon the product we required, so we can use our, like we can take our reagent like Gilman's reagent. For example, for preparation of butane from methyl chloride. So methyl chloride to butane conversion. So what is the respect to Gilman's reagent we can use? See, butane contains 4 carbons, but in methyl we have only 1 carbon, so 3 more carbon chain, I mean propyl is required. So you can say dipropyl lithium cuprate is useful reagent for conversion of methyl chloride to butane. You can answer. I hope it is clear. Let's move forward. Okay. Next, from carboxylic acid to alkanes. I mean carboxylic acids are converting into alkanes. Okay, so how can we do this? The first method is by decarboxylation. So let us say I have this carboxylic acid. Okay, so carboxylic acids, upon treating with soda lime means so like base NaOH plus CaO. So when we are treating with this, so we are getting respect to alkane. So we will be getting respect to alkane like RH. So for example, it is like acetic acid. What do we mean by acetic acid? CH3COOH. You can also call it as ethanoic acid. What I am saying? Acetic acid is a common name, or IUPAC name you can call. So 2 carbons are there. Therefore, ethanoic acid also you can call. Okay. So these upon treating with NaOH and CaO. So what happens here? So one thing you can remember, just remove this part. This is a, like, you can understand in the easiest way. This is the easiest way to understand, or the trick you can say. So CH3H is there, na? So just connect that CH3H like this. Okay. Otherwise, so what is the byproduct here? It is forming Na2CO3. What is that? Na2CO3. So how we are getting this? See, CO, here CO2 gas is liberating. So and here we have Na. So these 2 moles Na2CO3. Actually what happens here is, when we have this carboxylic acid, see, it is in basic medium now. First it converts into respective carboxylate ion. See, acid base reaction takes place and forms some salt like this. See, H plus it will remove, O minus, Na plus. So this is a sodium salt of carboxylic acid. So this, upon treating with NaOH plus CaO. So just remember here, so what we are doing, see this part you remove. So what is the remaining thing we have? This methyl and this hydrogen will be getting CH3 and this hydrogen, which is methane. So this is how we can prepare like respective alkanes from that carboxylic acid. So one thing you need to observe here, see, I have removed, see, in the starting material how many carbons are there? 2 carbons are there. In the last product we have 1 carbon. It means the product is having 1 carbon lesser than the starting material. So here we can say 1 carbon is less when it comes to the product. So I can write NC carbons converts into N minus C carbons. So reactant will be having, if it is having N number of carbons, product will be having N minus 1C, I mean 1 carbon is less. So I am writing here it has N minus 1C carbon. This is a change we are observing here. So for example, here I am writing like this. Now tell me, just simple NaOH plus CaO and heating. So this is how they will mention. So what we need to do, I told you, just remove this part and take the remaining part. It means how many carbons it is having initially. So 1, 2, 3, 4 carbons are there. So you should call it as butanoic acid. What is it? The IUPAC name is butanoic acid. So upon removing the CO2, decarboxylation we are saying, na, it means CO2 gas you are removing. So what is the remaining part? 1, 2, 3. 3 carbons are there. So propyl and add this hydrogen. It becomes propane. So it will be CH3. Just you can write in this form. No? Yeah, this is our product. I hope it is clear. Okay. 1, 2, 3. These 3 carbons are there. That's why respective alkane is like this, propane. I hope it is clear. Now here I am writing 2 different carboxylic acids. For example, here I am writing OH and it is containing here one keto group. Okay, this one, and another one is OH, and here it is having some alkyl group like CH3. So AB. So out of these 2, which is more which is involved in this decarboxylation easily, which is undergoes decarboxylation easily or readily. So how can we say this? So decarboxylation, so I can write here decarboxylation takes place more easily or more readily in electron withdrawing group containing carboxylic acid. So which carboxylic acid is containing electron withdrawing group? Acid. So here you can see this is having electron withdrawing group now. So electron withdrawing group containing carboxylic acids are readily involved in decarboxylation when we compare with the electron releasing group containing like carboxylic acid. Why? Because so when we are removing this part, see the carbon is getting negative charge on this carbon. So that will be stabilized by this electron withdrawing group. Therefore, electron withdrawing group containing like carboxylic acids are readily involved. Therefore, which is more reactive? A is more readily reacts in this reaction than this B. I hope it is clear. next now tell me, for these two questions you have to answer now. Yeah, see here, what is the product formed in this reaction? So in this reaction, acetic acid with NaOH and CaO, soda lime we can say. So this gives respect to hydrocarbon, like I mean remove this CO2 part, what is the remaining part? CH3H, methane is produced, but they are asking homologous of methane. It means next one, next carbon, that is ethane they wanted to get as a product, but it is giving methane, so this is not the correct. I hope it is clear. Next, for this compound A upon heating gives propane. So if you heat this, so you are not going to get propane. So if you heat this compound A upon heating with soda lime, CaO, NaOH. Yeah. So see here, what I told you, we need to remove this CO2 part. If we remove this CO2 part, what is the remaining part we have? CH3, CH2, one more hydrogen. So this is ethane only now. So they are asking about propane. So this is also not correct. So if you go for option C, how many carbons are there? 1, 2, 3, 4. So 4 carbons are there. So we can say butanoic acid. So butanoic acid means 4 carbons. In decarboxylation what happens? So 1 carbon will be less. So 4 becomes 3. So 3 carbons alkane is propane. So that is our answer. So remove this CO2 part, remaining is CH3 like this. So this is our option C is correct for this particular question. I hope it is clear. Next one is coal base electrolysis. This is also one of the very important process. So salts of carboxylic acids, like salts of carboxylic acids upon electrolysis gives alkane or forms alkane as product at anode, where the product is formed anode. At anode the alkane product is formed and alkane. So at anode product is formed. This statement you need to remember. And H2 gas released at cathode. Just remember these points. We will discuss about this mechanism. Okay. So for example, I have a carboxylic acid. So CH3, CH2, COOH, let us say. So this is a carboxylic acid we have. Okay. So this carboxylic acid, okay. So upon treating with some bases, what happens? It will form neutralization reaction takes place and form some salt. So what I am saying, sodium salts of salts of carboxylic acid, whatever the salt it is. Okay. So here let us say sodium salt of carboxylic acid like this. Okay. Upon electrolysis, it means we are taking this and we are electrolyzing. We are keeping it for the electrolysis process. Okay. So when it is subjected to electrolysis, what happens in electrolysis? We have two electrodes. One is anode and other one is cathode. So anode attracts the anions. It means it is positive electrode. Okay. So what is the anionic part here? So anionic part is CH3, CH2, CO, O minus, right? Okay. So what is the cationic part here? Na plus. So I am saying sodium salts of carboxylic acid. Okay. So in this solution we are also having at cathode. Just write this at cathode. So what is the cation we have? Sodium plus. Okay. Now in this solution we are also having, when I am saying solution, it also contains water, na? So water consists of H plus from water. Okay. Now look here, at anode what happens is loss of electrons, that is what oxidation takes place. So oxidation takes place at anode. This point you should remember. So loss of electrons, how it is taking place? See, the negative charge is there, na? So during electrolysis this charge breaks into like 2 electrons. I mean 1 electron is lost over here and it will generate a radical like this. O, this negative charge become radical like this. Okay. So 1 electron like lost from this, I mean released from here. So this released electron will be taken by this H place, okay, when we have 2 moles of H place, and 2 electrons will be taken and it will be releasing H2 gas. So H2 gas is released at cathode, okay, and at anode, look here, so it is a radical now. So this radical contains 1 electron, here also in the bond 2 electrons. See, this radical will pair up with one of this electron and giving us, see what it is giving, so giving us CO2 gas, CO2 gas, like this electron pairs and forms a bond like this, CO2 gas is released. So I am writing it as CO2 gas, CO2 gas. Along with this, so what is the remaining thing we have? CH3, CH2 and 1 dot electron, okay. So these compounds, I mean this one, like this, in this electrolysis process there will be n number of molecules, will, like if you take n number of molecules, so all will be converted into these forms now, okay. So now this will combine with the other molecule, like that the coupling takes place and results to give CH3, CH2, and one more thing, it will couple with the one more thing, like one more species like this, and will form CH2, CH3. If you are taking n number of carboxylic acid, n number of radicals are formed, so that will be like 2 will combine to form a one bigger molecule, no? So it becomes n by 2 number of products. So these things happens at what? At anode by oxidation, okay. At anode oxidation happens, and what are the products formed? The alkane is formed at the anode and CO2 gas is also released at the anode. I hope this is clear, okay. Next, so for example, if I say acetic acid is taken, sodium salt of acetic acid I have taken. So upon coal base electrolysis, tell me what is the product? Coal base electrolysis, tell me what is the product? So just here directly you can remember this. This is a complete mechanism, that is also not required. So just remember this, just remove this CO2. CO2 gas is released at anode, CO2 you write, okay. Then next, what is the alkyl group? Here we have alkyl is methyl now, so make it double, I mean couple it. So we will be getting CH3, CH3. So these two things are formed at anode, okay. And one more, at cathode we are getting H2 gas. What we are getting? H2 gas. I hope it is clear, okay. Now see here, H plus is converting into H2 gas, okay. This is what you need to remember, this is at cathode. So they will ask this, that's why I am highlighting all the times which is anode, where it what happening at cathode and anode, okay. Let's move forward. Read this, sodium acetate on coal base electrolysis gives ethane. Is this correct or not? Yeah. So just now we have seen here na, sodium acetate on coal base electrolysis gives ethane. Yes, it is correct, okay. And methyl free radical is formed at cathode. Where it is formed? Methyl free radicals. See, these free radicals are forming at alkyl free radicals are forming at anode, not at cathode. Therefore the second statement is incorrect. Only assertion is correct, reason is false. So where we have, see, A is true, B is, R is false. So option C is correct. I hope it is clear. Next, which one of the following reaction gives the product which is less number of carbons than the starting materials? Yeah. So this story I told you during one chemical reaction, that is what? Decarboxylation. What I told you, if NC carbons are there, n number of carbons are there, that converts into n minus 1C number of carbons. If there is 5 carbons, converts into 5 minus 1, 4 carbons will be there in the product. So this conversion takes place only in decarboxylation. So that is nothing but CaO plus NaOH. That is what? Decarboxylation using soda lime. So here option B will be the best suitable answer. I hope it is clear. Okay, in remaining all the cases, see, dry ether, sodium in dry ether with alkyl halide coupling takes place, RR product. Carbons are increasing, not decreasing. Electrolysis also RR product will be obtained. So this one will be giving RR here also. All these cases number of carbons are increasing, but in B it is decreased, one carbon will decreases. Okay, I hope it is clear. Next, We will come back to this after some time when we are studying about substitution reactions. Yeah. Next, coal-based electrolysis of sodium propanoate, right? Propanoate means what? How many carbons should be there? 3 carbons should be there. Sodium propanoate. Yes, this is a sodium propanoate. Okay. The products formed at the anode and the cathode respectively. Yeah. So when we are electrolysis, when we are subjecting to electrolysis, what are the products formed? See what I told you. Remove the CO2. Remove the CO2 in coal-based electrolysis. Coal-based electrolysis. So remove the CO2. What is the remaining part? Ethyl. So this ethyl free radical will be generated. So when these ethyl free radicals are generating, so I told you couple them. When free radicals are generated, just couple them, like add one more ethyl group, therefore we will be getting butane. So this butane is formed at anode. Alkyl product like alkanes are formed at anode. Yeah. Then next the product formed at anode is butane. Yeah. So only in option C it is there, we can directly choose. And also we know at cathode, we know H2 gas is released at cathode. Yeah. So based on whatever we discussed, the question will be there. Yes or no? Yeah. So H2 gas is released at cathode and product formed at anode. I hope it is also clear. Next, a mixture of ethyl iodide and N-propyl iodide. So I told you this is nothing but Woods reaction. See, methyl iodide, ethyl iodide. Methyl iodide, this is ethyl iodide, another one is N-propyl iodide. So like this, iodide is taken. So Woods reaction, what is the product formed in the Woods reaction? Woods reaction, we are taking sodium in dry ether. Yes, we know this is two different alkyl groups, alkyl halides. So here this ethyl can combine with itself and form the longer chain ethyl that is nothing but butane. Okay, this propyl can combine with itself, we are getting propane that is hexane, 3 carbons 6 hexane we are getting. This is butane, this is hexane, and when these are cross coupling, here 2 carbons are there, here 3 are there, so we will be getting pentane. What we are getting? Pentane. So these are the 3 different types of products we can expect. Now look at the options. The carbon which will not be formed. Yeah, butane is formed, propane is not formed, pentane is formed, hexane is also formed. So propane is not formed in this reaction. I hope it is also clear. The next, yeah, so you can take the screenshot of this. Then next we will be discussing about, yeah, answer this question. Woods reaction of bromoethane gives N-butane, sodium, salt. Okay, so Woods reaction of bromoethane, yes, so you can write bromoethane means C2H5Br. Woods reaction means treat with sodium metal in dry ether. Okay, so what they are saying, it gives N-butane. So we know coupling it, so we will be getting butane, N-butane. Sodium salt of X, okay, there is some sodium salt of this, some compound X is there. Okay, upon heating with soda lime, so it means decarboxylation reaction with the CaO heating, also results to form butane. So that is also gives butane. So identify X here they are saying, easy. So we know in decarboxylation the conversion will be NC carbons to N-1. If there are 5 carbons, we will be getting 4. It means in the product we have butane, it means 4 carbons are there. So reactant should contain 5 carbons and that must be carboxylic acid. So straight chain carboxylic acid. I mean there should be butane chain should be there. To that one carboxylic acid group should be attached. So look here in the first option, how many carbons are there? 1, 2, 3, 4. This is not the correct, because product is having 4 means reactant must have 5 carbons. So here you can see 3 carbons here, 4, totally 5. So this we have chance and go for this. See here we have 1, 4. I mean 1 here, 4, 5, this is 6th. So totally 6 carbons are there. So product should contain 5. This is not the one. Okay, there is some chance for B. Next, so here you can see only 3 carbons are there. So upon decarboxylation gives it 2 carbons only. It means this is also not correct. So only option B will be most suitable, because see here, how many carbons are there? CH3 means 1. Next here, methylene groups are 3 are there. CH2 here they mentioned it as 3 now. Here they mentioned it as 3. Okay, so CH3, CH2, CO, OH. Now decarboxylation means removing this CO2. Therefore, we are remaining with this chain, that is nothing but butane. So this is our product. I hope every question, like whatever we discussed, everything in our whatever we learn in the theory, okay, all questions are based on our discussion only. I hope this session will be highly helpful. So once again you go back through the content again. If you have any difficulties, look into it again and make some notes and try to solve these questions. Okay, if you have any difficulties, you can write in the comment box, we will be discussing them. So hydrocarbon A reacts with bromine by substitution, to form alkyl bromide. So to form alkyl bromide, some RX, let us say RBr I am writing, RBr, okay, which alkyl bromide, which by Wood's reaction converted into gaseous hydrocarbon. So by Wood's reaction converts into some product X, okay, converted into product X, which is gaseous hydrocarbon containing less than 4 carbon atoms. Yes, containing less than 4 carbon atoms they are saying. It is also easy. See, we haven't studied all these things, but we can apply using our common sense. See, product should contain how many carbons? Less than 4. Okay, now if we are taking the first option, so tell me what happens there. So let us say if our A is 1, see, substitution means remove one of this hydrogen, replace with like this group halogen, so Br. So we will be getting CH3, CH2, Br. So this is what the substitution. See, one hydrogen is substituted by this bromine, that's what ethyl bromide we got as a substituted product. Now when we are doing Wood's reaction for this, okay, Wood's reaction, what happens? This alkyl group will be doubled. It means it coupled with itself, and we are getting 4-member ring. So what he is saying, the hydrocarbon, the product should contain less than 4 carbons. It is having 4 carbons. It means first option is not correct. Remove that. Then next step, when we are doing for this second option, so when we are adding Br, so we need to add Br over here, because the pi bond is in a like pi electrons. So that will be when we are doing for this double bond. So we have to add at the both carbon atoms of these double bonded carbons, I mean alkene carbons. So here like this. So if you do Wood's reaction again, so it may get multiple, like 4-member ring we may get. So like that happens here. So but if you take fourth option directly, so methane upon treating with bromine we will be getting methyl bromide. So this upon Wood's reaction we will be getting ethane. So this is the most suitable answer for this particular question. So you can go with option number 4 for this question. I hope it is clear. Okay, same story which we studied for 2 will be applicable for 3 also, similar one. Next, which of the following statement is correct in the given coal base electrolysis? Yes, try this question. So give a try for this. Yeah. Which of the following statement is correct in the coal base electrolysis? Hydrocarbons containing even number of carbon atoms are produced. Yes, at anode. Yes, because see, even if I take Rx, it means it is containing, let us say, only 1 carbon it is having. So in coal base electrolysis, coupling takes place and produces RR type product. It means even number of carbons are there. Okay, even if I take 2 carbons, it will be giving 4 carbon product. If I take 3 carbon, it will be giving 6 carbon product. See, if we have like this, what they are taking? Coal based electrolysis, no? Yeah. So coal based electrolysis, if we are having RCOOH, okay, or ONA, okay, let us say here we have 2 carbons, the product will also be having 2 carbons now, because we are removing this part and we are joining this RR, we are making the coupling of this RR. So it is having 2 carbons, if we can say like that. Okay, now let us say there are 3 carbon product carboxylic acid like this. So odd number of carbons are having, but after removing this we will be having these 2 carbons now. Yes, so again we need to couple that, so we will be getting a 4 carbon product. Yeah, so whatever you are doing, we are getting only even number of carbons product in coal based electrolysis, and it is at anode. Yes, that is true statement. Next, hydrocarbons containing odd number of carbons produced at anode. So we will never get this odd number of carbons in this like decarboxylation reaction, coal based electrolysis process. Okay, next, hydrocarbons containing even number of carbons. See, products will not be formed at a cathode now, so no need to discuss about C and D. So most exact answer or most correct answer will be 1 only. Okay, I hope it is also clear. Okay, then next let's move forward. Sodium acetate on coal based electrolysis gives ethane. Yeah, so sodium acetate on coal based electrolysis, coal base. So what it will be giving? So I told you to remove this part, and we have methyl radical, so couple it. So it means we are getting a product like this. So whatever the alkyl group is there, so make it double, that will be our product here. Okay, now what I told you, when we have alkyl group, make it double, that will be our product. Okay, now that is the general case. Now look here, so I just want to give this COONA plus minus CO minus Na plus. Yeah, so will you try for this in coal based electrolysis? What is the product formed? Yes, so we can easily expect that. So this is only 1 mole I have. I am not taking 2 moles of alkyl halides, this carboxylic acid, I am taking only 1 mole. So in this case what happens is, see, if we are removing this, so we are getting this CO2, if we remove, we are going to get a radical over here, and after removing this, we are going to get a radical here also. So now we are getting something like this, 1 radical here, 1 radical here. So make a bond out of it. So our product is hexene, cyclohexene, like this is our product. I hope it is clear. Okay, so generally what I am saying, when we have like carboxylic acid, alkyl group is there now, so take the 2 alkyl groups and merge it, that will be our product. Okay, next, identify here. Yeah, this is already done. Next question here, which one of the following reaction gives product less than, yeah, this is also done. Yeah, reduction with, okay, so reduction with red phosphorus and iodine, like HI, hydrogen iodide and red phosphorus. This mixture, when we use, see, reduction of alcohols, carbonyl groups, carboxylic acid. See, alcohols, aldehydes or ketones and carboxylic acid, when we are using HI and red phosphorus, so this will be giving respect to alkanes. So whatever you are taking over here, so when we are treating with HI and red phosphorus, gives respect to alkane. If it is ROH, it will give RH, like that, like CHO is there now, so that carbon converts into respect to like methylene group or like alkyl side. Yeah, so here one more thing, this is important again. So remaining thing we will be discussing in the upcoming class. So this is our last topic here. So when we have ketones or aldehydes, what I am saying, when we have ketones or aldehydes, so when we treat this, see, from aldehydes and ketones converting into alkanes, respect to alkane, like this. Okay, this is the alkane, ketone and aldehyde. So any of this ketone or aldehyde. So when we are using zinc amalgam ZnHg in acidic medium like HCl like this, so we will be getting our respective alkane. So just convert whenever you are seeing this reagent zinc amalgam and acid, so just remove, I mean just convert this C11O group into CH2 group. So this is what the change happens in this process. Okay, so I will be giving you, see mechanism here, no discussion of mechanism will take too much of time, and even in the exam point of view you need to know the process, what happening here, what is the exact use of this reagent. So this reagent converts carbonyl groups to respective alkanes. So what process name is Clemmensen reduction. Yeah, this is enough. Okay, so here I have like this. So I want to convert it into this form. So what we need to do? So just use here Clemmensen reduction ZnHg HCl. That's it. So you should say zinc amalgam and in acidic medium. That's it. Okay. Next, similar kind of reaction will be there, Wolff-Kishner reduction. So Clemmensen reduction we are using in acidic medium. So Wolff-Kishner reduction is useful in basic medium. So here we will be taking same. So let me take in a generalized manner. So I am taking here ketone or aldehyde. So upon treating this with hydrazine, NH2, hydrazine, it is in alkaline medium like KOH, and upon heating, so this CO group is there now, this carbonyl group converts into respective alkanes like this, like here you just replace with hydrogen like this. So this is our product. So CO, like whatever the CO group is there now, converts into CO groups converts into CH2 group. This is the conversion happening in both Clemmensen and Wolff-Kishner reduction. Wolff-Kishner reduction we are using hydrazine in basic medium. What is this? Alkaline medium, and heating condition is required. There Wolff-Kishner reduction is basic medium, hydrazine is used. In Clemmensen reduction zinc amalgam in acidic medium. Here it is basic, there it is acidic. This is the main difference. So when we need to use like which kind of reaction, for example if there is any acidic sensitive group is there, for example here I have this group I have, and here let us say here I have one alcohol group is there. So I just want to convert this ketone like this aldehyde group into alkane form. I mean I need to convert this into CH3 OH. So I need to convert into this form without disturbing this OH group. Okay. Now if I use this like Clemmensen reduction, what is that? Zinc amalgam in HCl and HCl like this. If I use Clemmensen Wolff-Kishner reduction, we need to take this reagent. So what happens here when we are using above one and below one? So when we are using this acidic group, this group will be getting disturbed. This is the acidic sensitive group. Therefore if we use this, reaction takes place at this place also, like OH will be removed and Cl will be occupied in this position. So it means that conversion is not fruitful, right? So we need no disturbance at this OH, we need only conversion of carbonyl to alkane, but it is not happening because the disturbance is taking place here also, right? Therefore this is not the suitable one. So we need to use only Wolff-Kishner reduction but not Clemmensen reduction for this particular process. So based on the requirement during the chemical reactions, we will be taking the selective like reagents for that particular conversion. I hope it is clear. So only Wolff-Kishner is favored in this case, not Clemmensen. Okay. Then next, yeah, let us wind up with this final discussion. So remaining things we will be discussing in the upcoming class along with the PYQs. Okay. So alkanes, see alkyl halides with lithium aluminum hydride, sodium borohydride we discussed gives respective alkane, like see gives respective alkane. Just remove Br and replace with one hydrogen. Okay. Replace with one hydrogen, that will be the respective alkane. See, now I also told you when we are using this zinc, so zinc So this is one more reaction. Zinc in basic medium also you can take. So that is also giving respect to alkane, just remove this bromine. Okay, next Wood's reaction, which we already discussed very clearly. So alkyl chloride is given, remove this chlorine and replace it with RR. That will be our product. Franklin reaction also I told you, like R, so what I told you here, RCl if it is there. So treat this with zinc, see here it is given. So treat this alkyl chloride with this Franklin zinc metal, therefore we will be getting R as a product when we are taking 2 moles. Okay. Then next Gilman's reagent, what I told you, alkyl halides with dialkyl lithium cuprate. So that is what the carry house synthesis, and the reagent is called Gilman's reagent. We will be getting respect to alkane as a product. Okay. Next what I told you, the next thing is, so this alkene process we haven't discussed, we will be discussing in the hydroboration of alkenes the upcoming class. Okay. Next one more thing is, so alkenes upon hydrogenation gives respect to alkanes. That is what here the 2 reactions indicating here. Okay. One more here, so hydrazine with H2O2. Okay, this is also one of the important one. So transfer of hydrogen. So here alkene converting into alkanes. Okay, so this is about the discussion. Okay, so this take it as a homework. So hashtag question number 1. So in the comment box I want answer for this, so mention it as hashtag 1 and give the answer. Just match them. Soda lime and decarboxylation, what is the reagent used, like that you match it and tell me in the comment box. I will be waiting for your answer. If any confusions or any difficulties are there, write in the comment box, we will be discussed there. Okay, so thank you for watching. Happy learning.